Picture the recommendation system behind a platform like TikTok or Kuaishou. When you open the app, somewhere in a data center, a cascade of models springs into action. First, a retrieval stage scans through millions of videos and pulls out maybe 10,000 candidates. Then a pre-ranking model trims that down to a few hundred. Then a heavy ranking model scores those few hundred and picks the handful you actually see. Each stage is its own model, trained separately with its own quirks and bottlenecks. And here's the catch: the quality of what you see is fundamentally capped by the quality of the earliest stage. If Retrieval misses a great video, no amount of clever ranking downstream can save it. The paper we're looking at today, called OneRec from the team at Kuaishou, asks a bold question. What if we threw out the entire cascade and replaced it with a single generative model that directly produces the list of videos you should watch next? Not a model that scores candidates one by one, but one that generates the recommendations the way a large language model, LLM, generates a sentence, token by token. And remarkably, they got this to work in production, serving hundreds of millions of daily users with a 1.6% lift in watch time, which at that scale is a very big deal. To set this up, let's quickly cover what came before. Prior generative recommendation work, like a system called Tiger, took the idea of representing each item as a short sequence of discrete semantic tokens, kind of like assigning every video a 3-character codename derived from its content, embedding. Then they trained a transformer to auto-regressively generate the codename of the next item a user might like. Think of it like text generation, but where each item is a small word made of a few subword tokens. The problem was that these systems only matched the quality of the retrieval stage, not the full cascade. They were a clever way to fetch candidates, but you still needed all the ranking machinery on top. OneRec rethinks this in 3 important ways. First, the architecture. They use an encoder-decoder transformer similar in spirit to T5. The encoder takes in your history of watched and liked videos, each represented as a sequence of semantic tokens, and produces a contextual representation. The decoder then generates the recommended videos token by token. To scale up without blowing up compute, they use mixture of experts, MOE, layers in the decoder's feed-forward blocks. The idea is that instead of every token activating one giant feed-forward network, the model has many smaller expert networks and a router sends each token to just 2 of them. So you get the representational capacity of a much larger model while only paying the compute cost of a small one. At inference time, only about 13% of the parameters are actually active. Now, before we get to the second contribution, a quick word on how they tokenize videos. They take a multimodal embedding for each video and apply residual k-means quantization across 3 layers, with 8192 clusters per layer. So every video becomes a 3-token sequence, almost like a hierarchical address. But here's a subtle detail that matters in practice. Vanilla k-means produces wildly imbalanced clusters, the so-called hourglass phenomenon where a few tokens get used constantly and others almost never. They fix this by forcing every cluster to contain exactly the same number of videos, assigning items to centroids in order of distance while respecting that quota. This balanced codebook is crucial for the generative model to actually learn diverse outputs. The second key contribution is session-wise generation. Traditional next item prediction generates one item at a time, and then you need handcrafted rules to combine those items into a coherent list, things like ensuring diversity or avoiding repetition. OneRec instead generates an entire session of 5 videos in one autoregressive pass. The training data consists of high-quality real sessions, defined by criteria like the user watched at least 5 videos in the session, total watch time exceeded a threshold, or the user liked, shared, or followed someone. By training on these golden sessions, the model implicitly learns coherence, ordering, and diversity from data rather than from rules. Think of it like the difference between teaching someone to write essays by giving them a list of sentence templates versus giving them great essays to read and imitate. The latter captures structural patterns the former never could. The third contribution is where it gets really interesting: aligning the model to user preferences using direct preference optimization, DPO, the same technique used to align LLMs with human feedback. But there's a fundamental challenge. In language modeling, you can ask a human to compare two responses and pick the better one. In a recommendation system, the user only sees one set of recommendations per request. You never get a true side-by-side preference. So how do you build preference pairs? OneRec's answer is to train a separate reward model that predicts how much a user would like a given session based on signals like predicted watch time, view probability, follow probability, and like probability. The reward model is trained on abundant historical interaction data and uses target attention plus self-attention over the items in a session to produce multitask predictions. Then, for preference alignment, they take the trained OneRec model, run beam search with a beam size of 128 to generate many candidate sessions for a given user, score each one with the reward model, and pick the highest scoring as the chosen response and the lowest scoring as the rejected response. These become the preference pairs for DPO training. It's a kind of self-improvement loop. The model generates its own candidates, the reward model judges them, and the best and worst get fed back to push the policy toward better outputs. A clever efficiency trick is that they only apply DPO to 1% of training samples. The ablations show that going up to 5% gives only marginal gains while using 5 times more GPU resources, so 1% hits the sweet spot. And the iterative aspect matters. As the model improves, it generates better candidates, which produce better preference pairs, which further improve the model. On results, OneRec at 1 billion parameters outperforms strong baselines like SassRec, BERT4Rec, and Tiger on every metric they track, including session watch time, view probability, follow probability, and like probability. Adding their iterative preference alignment on top gives another meaningful boost. And crucially, their version of preference optimization beats other DPO variants like IPO, CDPO, CMPO, and SDPO. They also confirm clean scaling behavior. Going from 50 million to 1 billion parameters consistently improves performance. In the online A/B test on Kuaishou's main feed, OneRec with preference alignment delivered a 1.68% increase in total watch time and a 6.56% increase in average view duration per video, replacing the entire multi-stage cascade with this single model. Now for the honest limitations. The authors themselves note that while watch time improved dramatically, interactive signals like likes did not improve as much. This hints that the model is great at predicting passive engagement, but weaker at capturing the more nuanced behaviors that signal deeper interest. There's also a deep dependency on the reward model. If the reward model is biased or miscalibrated, the preference alignment will faithfully push the policy toward those biases. And while the encoder-decoder with MOE is efficient, beam search with size 128 at serving time is still non-trivial latency-wise compared to a sharded retrieval index. Finally, the approach inherits all the cold start challenges of semantic tokenization. A brand new video has to first get a meaningful multimodal embedding before it can be tokenized and recommended. Now let's walk through some questions you might have after hearing all of this. First, why does generating an entire session at once actually work better than generating one video at a time? The intuition is that videos in a good session aren't independent picks. A great session has rhythm, variety, and momentum, where each video sets up the next. When you generate point by point, every choice is locally optimal, but globally incoherent, and you end up bolting on rules to enforce diversity. When you generate the whole session auto-regressively, the model can plan the second video knowing what the first one was, learning structural patterns from real successful sessions directly rather than approximating them with heuristics. Second, isn't using a reward model trained on past interactions just going to reinforce whatever the old cascade system was already doing? This is a real concern. The reward model is trained on logged user behavior, which was shaped by the old system, so there's a feedback loop risk. What makes it work in practice is that the reward model predicts fine-grained outcomes like watch time and likes, not just whether something was shown. So it captures something closer to true user preference rather than just imitating the old policy. Still, the authors would likely need ongoing fresh data and possibly off-policy correction techniques to avoid the model drifting into a narrow attractor over time. Third, why use mixture of experts instead of just making a denser model bigger? The economics of recommendation are brutal. You're serving billions of requests a day, so inference cost dominates. A dense 1 billion parameter model would require activating all 1 billion parameters for every token generated. With MoE, only about 13% of those parameters fire per token, so you get the modeling capacity of a big network at the compute cost of a much smaller one. This is exactly the same trade-off that makes MoE attractive in frontier language models like Mixtral, just applied to a domain where latency budgets are even tighter. So how do these ideas apply to large-scale recommendation systems beyond Kuaishou's specific deployment? The most exciting practical takeaway is that the retrieve-rank-re-rank cascade, which has been the dogma in industry for over a decade, may finally have a credible alternative. If you can train a single generative model that does the job end-to-end, you eliminate entire teams' worth of pipeline complexity, the constant feature mismatch between stages, and the upper bound problem where bad retrieval kills good ranking. For production teams, the immediately portable ideas include the balanced semantic tokenizer, which addresses a real failure mode in any vector quantization approach, the session-wise generation framing for surfaces that show multiple items at once, like home feeds and shelves, and the reward model-based DPO loop as a general recipe for preference alignment without needing explicit human labels. The harder open challenges are multi-objective optimization, where you need to balance watch time, likes, creator diversity, and long-term satisfaction simultaneously, and the cold start problem for new items and new users. But this paper is a strong signal that the next generation of recommenders will look much more like language models, generating recommendations as structured sequences than like the elaborate ranking cascades we've built for the past decade.